Welcome guys to the new video. In this video we will discuss about the torsion, uh, the effects of applying a torsional load to a long straight member such as shaft or tube, or if we talk about in civil engineering beams especially, right? Initially we will consider the member to have a circular cross section. Okay, we will show how to determine both the stress distribution within the member and the angle of twist. So there will be two main portions of this lecture: the stress distribution and the angle of twist, right? And after that I will go to the non-circular cross sections, because in civil engineering beams columns they are most of the time non-circular, right? So let's start with the lecture. The torsional deformation of a circular shaft. Torque is a moment that tends to twist a member about its longitudinal axis. Okay, so this is a circular shaft, right? And you when you apply uh, some force, some twisting force, right, either on one end or both the ends, then it will be causing twisting. For example, if I twist it in this direction, right, from one end, and I twist it in opposite direction from the other end, right, so that will cause the torsion in this shaft. Its effect is of primary concern in the design of drive shafts used in vehicles and machinery, especially in mechanical engineering. And for this reason, it is important to be able to determine the stress and deformation that occur in a shaft when it is subjected to torsional loads. Okay, we can physically illustrate what happens when a torque is applied to a circular shaft by considering the shaft to be made of a highly deformable material such as rubber. So the example that I have shown you, in this example they are considering it as a rubber element, right? When the torque is applied, the longitudinal grid lines are, so these longitudinal grid lines originally marked on the shaft, okay, tend to distort into a helix. So let me take you again. See, these longitudinal grid lines, these are turned into helix, where there the dimension is small and here the dimension is large, right? See here. So also all the cross sections of the shaft will remain flat, that is, they do not warp or bulge in or out, and radial lines remain straight and rotate during this deformation. So during this deformation, the radial lines, these radial lines will remain straight, and only these longitudinal lines, see, the longitudinal line is not straight, it has been twisted, right? Initially it was straight. So provided the angle of twist is small, then the length of the shaft and its radius will remain practically unchanged. If the angle of twist is small, then the length of the shaft and its radius will remain practically unchanged. But if the angle is large, then it will affect the length of the shaft as well as its radius. Okay, so notice the deformation of the rectangular element when this rubber bar is subjected to a torque. This is uh, before application of the twisting or the torque, and this is after. So check the deformation in this rectangular element. Okay, now if the shaft is fixed at one end and a torque is applied to its other end, in this example the torque was applied to both the ends in opposite direction, right? But let me take you to this one. Here the shaft has been fixed from this side, okay, where the axes are lies, x, y and z. This is the x-axis, y-axis and z-axis. This side has been fixed and torque is applied to this free end. Okay, as shown in figure 2a, I have already showed you, will distort into a skewed form as shown, right? So it will distort in a skew form. Why it is skew form? Because here the angle of twist will be 0 where it is fixed, right? And as we move away from this fixed support, so the angle of twist will increase, so it will be in a skew form. Here a radial line located on the cross section at a distance x from the fixed end of the shaft will rotate through an angle phi of x, right? uh, if this is the fixed end and we are taking a section at this point, and the distance of it from the fixed point is x, So the angle of twist or the amount of rotation that the cross section will experience will be phi of x. Why it is in terms of x? Because it depends upon the distance from the x. At a zero distance, the phi will be 0, and at this distance the phi will be maximum. So phi totally depends on the this distance x. Okay, that's why we are writing phi in terms of x. This angle is called the angle of twist. This phi of x is basically the angle of twist, and it depends on the position x and will vary along the shaft as shown. As I show you that if x is 0, then at this cross section the phi will be 0, and if x is maximum at this point, the phi will be maximum, right? In order to understand how this distortion strains the material, we will now isolate a small disk element located at x from the end of the shaft, for example in figure 2b. So let me take you to the figure 2b, right? So this is a small disk that I has taken from here. This is at the distance x from the fixed support. So this disk has some thickness. What is the thickness? The thickness is d of x, right? And this is the center or middle of this shaft, right, where about which it is been rotating. The c is the radius of this shaft. If we take an element here at a distance rho, and we find this red line, if you can see this red line, this red line is basically the uh, shear strain in this disk at this point at a distance rho from the center or from the longitudinal line or longitudinal axis of this shaft, right? So due to deformation, the front and rear faces of the element would undergo rotation. It is quite understandable that when you rotate it, so the front will rotate more than the back, right? Because here rotation was 0 and here the rotation is maximum. So as you are coming along the length, the rotation has been increased. So along the thickness, the rotation at the back side will be less as compared to the front side, right? So the back face will rotate by phi of x, and the front face will rotate by the phi of x plus the change in the angle of twist, right? As a result, the difference in these rotations, that is the d of phi, causes the element to be subjected to a shear strain gamma. This is the picture from the chapter of shear strain, where due to shear force, the strain was induced, which was the change in the angle of the material, and that strain was calculated, right? Now we are done with this figure. I hope you have understand the basic terminologies and the basic principle. Let's continue. Now this angle or shear strain, as you know that shear strain is basically the change in angle of the material, can be related to the angle d phi. Now how we can relate the shear strain with the d phi? By noting that the length of the red arc, as I show you this red arc, its length is basically the shear strain, right? So in figure 2b we have noticed that red arc is basically the shear strain. So how we can relate it? Rho into d phi. Rho is the distance from the center line, and d phi is the angle, right? Will be equal to gamma into dx. So gamma will be equal to rho into d phi over dx. This is our equation 1. Since dx and d phi are the same for all elements, dx and d phi. D phi is basically the angle and dx is the thickness. So along this disk, the tx will remain the same, and same is the case for d phi, right? So therefore, then d phi over dx is constant over the cross section. So for this whole cross section, this d phi over dx will remain constant, and equation 1 states that the magnitude of the shear strain varies only with its radial distance rho from the axis of the shaft. So it means that if this term is constant, right? Let me show you. If this term is constant, then shear strain only depends upon this phi. It means that if phi increases, gamma increases. If phi decreases, gamma decreases. And what is phi? Phi is the distance from the neutral axis or this middle axis. So if something is lie over here, the shear strain will be 0, and if something lies here, the shear strain will be maximum, right? Then since d phi over dx is equal to gamma over rho, from this equation you can derive this, right? And gamma is maximum at maximum distance from the center, which is the radius, right? See, at here the gamma will be 0, and at c it will be maximum, right? So at c, if rho is c, then gamma will be gamma maximum. Then we can put here that gamma is equal to rho over c into gamma maximum, right? So in other words, the shear strain within the shaft varies linearly along any radial line from 0 at the axis of the shaft to a maximum at its outer boundary, right? So shear strain will be 0 here, and it will be maximum at the outer boundary, right? Now, keeping in mind the concept which is again presented here, let me bring the pointer. So when an external torque is applied to a shaft, this is a shaft, and external torque is applied to it, it creates the corresponding internal torque. So as you know that the action and reaction equation, and also the pressure and stress relation. So in the same way, if you applied some torque, then there will be some resistive torques. Okay, in this section we will develop an equation that relates this internal torque to the shear stress distribution acting on the cross section of the shaft. So we are going to develop some equation that this internal torque is related to the shear stress distribution. If the material is linear elastic, then Hooke's law applies, right? And we know from the shear stress equation that tau is equal to G into shear strain, or tau maximum is equal to G into maximum shear strain, and consequently a linear variation in shear strain, as noted in the previous section, leads to a corresponding linear variation in the shear stress. So if you can see from this equation that shear stress and shear strain are related with a linear equation. So from this equation, if gamma maximum gamma is maximum when rho is equal to c, so the same goes for the tau, right? So we can replace gamma in the previous equation with the tau. So tau will be maximum where rho is equal to c in this whole scenario. Since each element of area dA, for example, let me again take you, if the area, if we consider a small area dA, right, at a distance rho from the center, so there at the center the area will experience zero shear stress, and at the outer edge it will experience the maximum shear stress, tau maximum, and in between the distance will define what amount of shear stress it has been experiencing, since there is only simple relation which is rho by c, and rho is its distance from the center, right? Therefore uh, uh, the force is equal to area into stress, shear stress, and the torque produced by this force is then equal to rho times the force, right? The force which is dF into rho will equal to the torque produced. For the entire section we just integrate it over the entire section, rho into this dF, which is equal to tau into dA, and we are putting the values of tau. So tau is equal to rho by c into tau maximum. So rho by c into tau maximum, this rho and this rho will become rho square, and this c tau maximum over c is a constant, so we'll take it out. So torque is equal to tau maximum by c into rho square, and we are integrating it over entire area. So this term, this integral term, is the polar moment of inertia, which is represented by J. So if we have to find out the maximum shear stress, then we will take the C to the other side, it will multiply it with the T, and this J will go and divide it on the other side. So tau maximum is equal to TC divided by J. This is the basic equation for the stress and the torque. You can go through it, that what are these terminologies, and we can also substitute equation 6 into equation 3. This is your equation 6, tau maximum, and this is your equation 3 for tau maximum. If you put it for you will get for the tau that okay, the tau, or what will be the shear stress at any point. So again, it will depend upon the location from the neutral axis or the middle of the shaft. So tau rho by J is for the shear stress at any point, and tau maximum is for the maximum, which will definitely lies at the outer edge of the shaft. So what was the polar moment of inertia? If the shaft is solid and circular, so it has a radius of c. So putting these things, taking integration, and the final value will be J is equal to pi by 2 into C4. I am not going into details because it is of the engineering mechanics concept, and you better go and revise your concepts of moment of inertia and polar moment of inertia, right? Now J is equal to pi by 2 into C4 is for the solid section, and J is equal to pi by 2 C outer 4 minus C inner 4 is for the tubular or hollow section. So please keep in mind that which formula has to be used. The one more important thing, that the unit is the same as of moment of inertia, mm4 or inch 4. Now the shear stress distribution. If an element of material on the cross section of the shaft or tube is isolated, if you isolate this material, for example in figure 6a, right, and due to complementary property of shear, equal shear stress must also act on four of its adjacent faces, because we are just seeing a shear force or shear stress on just one side of this element, right? So let me show you. If this is the element and this is the force that have been shown to you, for example this force, right, or this force or stress, if it is acting on one phase, then equilibrium demands that summation of f of y means that an equal and opposite force should act on the opposite phase, right, to make it in equilibrium. But due to these two equal opposite forces, a couple has been generated, and to balance that, equal and opposite couple should be generated on the other two. So this was to say that on all the four adjacent sides of the element, this force should be acting. As a result, the internal torque T develops a linear distribution of shear stress along each radial line in the plane of the cross-sectional area, and also an associated shear stress distribution is developed along an axial plane, which is in figure 6b, right? It is interesting to note that because of this axial distribution of shear stress, shafts made of wood tend to split along the axial plane when subjected to excessive torque. Now you can see that the torque has been, or the stress distribution varies from the center, right? It is zero at the center, and it is maximum at the outer edge of this shaft, right? And in between it varies, but since it is varying radially, but the shaft, if you see in figure 7, is cracked, right? It's split along the axial plane and not in the radial plane. Why? This is because wood is not isotropic, it is an anisotropic material, and it has different properties in different axes, right? Whereby its shear resistance parallel to its grains or fibers directed along the axis of the shaft is much less than its resistance perpendicular to the fibers. So in this direction it is weak, and in this direction it is strong. Therefore it is cracked in this direction, right? This was an interesting thing. The important points, that when a shaft having a circular cross section is subjected to a torque, the cross section remains plane while radial lines rotate. We already discussed it. This is just a summary. You please go through this, and the procedure for analysis is already known, and let's jump to the example 1, and you will better understand how we can determine the things. Now the solid shaft and tube shown in figure 8. This is a solid shaft and this is a tubular shaft, right? So the J will be different for both of them. Are made of a material having an allowable shear stress of 75 megapascal. Now allowable shear stress is given, tau maximum, right? Determine the maximum torque T is required that can be applied to each cross section, and show the stress acting on a small element of a material at point A on the shaft. and points B and C of the tube. This is point A on the shaft, which is at the outer diameter, and this is point B and C. One is at the outer diameter and one is at the inner diameter, right? The polar moment of inertia for the solid and tubular shafts, we know the formulas. Pi by 2 into C4 is for the solid shaft, and pi by 2 C outer 4 minus C inner power 4 is for the tubular shaft. So we find this one out. Shear stress, the maximum torque in each case is, we know this formula, that tau maximum is equal to Tc by J, and tau maximum is given to us, which is 75 megapascal. So we are putting the values of tau maximum, which is equal to 75 megapascal. Mega means 10 power 6 and pascal is Newton per square meter. We have to find out this T, right? So T will remain as it is, and we know the C. Why? The 100 millimeter is equal to 0.1 meter, and we have determined J. So we will put the values of J. So the torque, value of torque is 118 kilonewton meter, right? And similarly for the tubular one, the value of T will be 80.5 kilonewton into meter. Also, the shear stress at the inner radius of the tube is, at the inner radius of the tube, the shear stress is, this is the value of torque, this is the value of its inner radius, and this is the value of its polar moment of inertia. So at the outer radius it is 80.5, and at the inner radius it is 56.2. So see, at the inner radius the shear stress is, or the torque is 56.2. Oh, sorry, it is the shear stress, not the torque. uh, the torque is 80.5 in this case, right? So you can determine the shear stress here as well, and in this case as well. The second example is about a 1.5 inch diameter shaft shown in figure 9a. This is 9a, is supported by two bearings. There are two bearings, right? And is subjected to three torques. Torque number 1 in anti-clockwise direction of 42.5, torque number 2 of clockwise direction 30 kip, and torque number 3 is in clockwise direction of 12.5, right? Determine the shear stress developed at points A and B, right, located at section AA and of the shaft in figure C. So this is your figure C, right? And you have to determine the stresses. Since the bearing reactions do not offer resistance to shaft rotation, the applied torque satisfies moment equilibrium about the shaft's axis. The internal torque at section AA, this is your section AA, if you are seeing it, will be determined from the free body diagram of the left segment. We consider the left segment to the AA. This is shown in figure B, right? This is your resultant torque. Why it is in clockwise direction? Because the 42.5 is in anti-clockwise direction and 30 kip is in clockwise direction. So a a resultant of 12.5 should be acting in this direction to make it in equilibrium, right? So the summation of moment in about x-axis is equal to 0, 42.5 in clockwise direction minus 30 in anti-clockwise direction, minus 30 in clockwise direction, minus t because it is also in clockwise direction, is equal to 0. So from this equation t is equal to 12.5. Now section property, we know that the J is equal to pi by 2 C power 4, and the shear stress, since point A is at rho is equal to C, so this is point A and here rho is equal to C, so it will be the maximum shear stress. So tau A is equal to Tc by J, which is equal to 18.9 ksi, and at point B, which is right here, right, this is point A and this is point B. So at point B, the rho is equal to 0.15, which is even less than half of this C. So we have T is same, J is same, but due to this rho, the shear stress reduces to only 3.77 ksi. So these are two of the examples that shows how we can find the section property for different geometries, and how we can find the shear stresses, for example in this case, and in previous example how we can find the torsion in different cases, right, where T was required. So this was all about the first section where we can relate the shear stress with the torsion, and we can find the section properties. In the next video, we will discuss about the angle of twist and all the details related to it. So thank you very much.